So chapter 3, section 3, implicit differentiation and related rates. Okay, so let's see what do those terms mean. Implicit differentiation. So to deal with equations, not functions, let's say we have this equation, x squared plus y squared equals to 1. If we graph this, that's a unit circle. That is a unit circle. So it's an equation, it's not a function. Right? It's not a function. So we cannot follow the rules for functions to differentiate. So that's why it's called implicit. So what do we do? Let's say we want to find a dy dx. Or same as y prime, right? Because we cannot solve for this. We could. If we solve for this, what do we get? We get two functions. So y, we get plus minus square root of 1 minus x squared. So we have to split this into two functions. Right? The top is a function, the bottom is a function. The top is a positive one, the positive one. The bottom is a negative one. So what do we do? So it's not a function. We cannot use the function, the differentiation for function to do that. So we use implicit differentiation, which means we take the derivative simultaneously with all the variables. In this case, we have two variables. Right? Of course, this can extend to 3 variables, 4 variables. So let's just talk about 2 variables. We have x, we have y involved. And we cannot write this equation as a function. So what do? We take derivatives with everyone simultaneously. So I'm going to use x prime, y prime for simpler writing, all right? So when I take derivative, when I take a derivative of this, so basically what I do is I do dx squared dx, right? So what do I have? I just have 2x, which is normal as functions. When I take y squared, first I'm going to do 2y, similar to a function, but then I multiply by y prime, or y prime, which is a dy dx, right? Because I'm looking for y prime. So in this kind of case, basically, we're trying to solve for dy dx. Of course, you can argue with me saying, well, maybe I want to find dx dy, same thing, all right? So by convention, we consider dy dx. Especially this equation is symmetric, where xy doesn't make any difference. So by convention, we like to talk about the dy dx or y prime. So that's our goal. We want to find the change of rate of y in terms of x. So how the change of x affect the change of y. So x squared derivative is 2x. Y squared derivative is 2y, but multiplied by y prime, or dy dx. So this is the implicit differentiation part. Then we take derivative with 1, or this derivative of constant with 0, because there's no rate of change, right? The constant doesn't change. Now we can solve for this y prime. So 2y, y prime, let's move 2x, or subtract 2x on both sides, and just get negative 2x. So then we divide by 2y on both sides, right? So y cannot be 0. So y cannot be 0, right? We cannot consider those 2 points. Y cannot be 0. Then simplify this. So y prime equals negative x over y. That's it. Okay, so that is the method of implicit differentiation. Implicit. So how is this different from before? Is we attach this y prime, so this one. Okay, let's see more. Let's see more examples. So this is the circle with radius 2. The one I use example is radius of 1. right? Let's see the picture. So when we consider dy dx, what is that? Okay. The rate of change of y in terms of x. You see, that's, if we talk about this point, so dy dx at this value, let's say at this a value, right? Dy dx at a will be the slope of this tangent line. Will be the slope of this tangent line. Same thing for every point. But y cannot be zero. You see what happens with this y equals zero? We have vertical lines. The tangent lines are vertical. So there's no derivative. But at any other points, okay, we can find the rate of change of y in terms of x. So at this point, right? At this point, we use the y prime. Remember, y prime equals negative x over y. Right? Let's see, we want to find at this point, right? What's the rate of change at 1? It is a negative x value is 1, y value is square root of 3. That's it. That's how fast this point, the speed. If you imagine that something is, you imagine, or maybe this circle is rotating, right? At this point, the speed is such. The rate of change is such. All right. Let's see more examples. We use this notation to mean evaluate, right? Once we find the dy dx, we make a bar, say evaluate such at x equals to a, y equals to b. It's just a notation. Right, again, let's see this example. We have x squared plus y squared equals to 4. We want to find a dy dx. Then we want to find the slope of the tangent line at the point, at these 2 points. So we just take a derivative simultaneously, right? So we start with x squared plus y squared equals 4. We differentiate every term. Differentiate x squared, we get 2x. Differentiate y squared, we get 2y. But then with y term, we attach, we multiply by y prime. So that's the difference than before. Then derivative of 4 equals 0. So we simplify, we solve, we see the rate of change is negative x over y. Then we can evaluate at the given points. So dy dx equals negative x over y. At this point, we just plug in. So that's that. At this point, we plug in. That's positive. So then everything, the rule we learned, everything follows. We still have product, we still have to do product rule, quotient rule, chain rule. Okay, we still have to do that. Let's see more examples. Let's see this one. So here we see product, right? We have product. We see x squared times y raised by 6. So we have to apply product rule. So which means we take a derivative of the first one, x squared is 2x. We multiply by the second one. Then we take a derivative of the second one, multiply by the first one. So I have x squared times 6 times y raised by 5. Then derivative of 1, just 0. Then, oh, something I forgot. Do you see that? I have to attach y prime here, right? Because when I take a derivative with y term, y raised by 6, there's a 6, y raised by 5, but then I have to multiply this y prime, or dy dx. I cannot forget about this. So then what do I have? I have y prime equals to negative 2xy raised by 6 divided by 6x squared y raised by 5. And we can simplify a little bit, right? 2, 6, cancel like that. X, cancel this. Y to the 5, cancel like this. So I have negative. So the numerator, we're only left with negative y. And the denominator, we have 3. So negative y divided by 3. So then we can evaluate. So oh, I forgot x. Right? 3x. Because I have x squared in the denominator. So negative y over 3x. So if you give me a point, x value, y value, I can evaluate. Let's see this one. Our goal is to find a dy dx. Right? We see product rule, right? So this one is easy, just negative 3. The other 5 is a 0. But this one, we have to, let's do this on the side. So x squared y, we want to differentiate this. That's my shorthand for differentiation. So differentiate x squared, I have 2x multiplied by y, then plus differentiate y, which is 1y, y prime, then multiply by x squared, right? That's this term. Then, so let's write here. So we have 2xy plus x squared y prime. Then plus similarly, differentiate x is 1, so I have y cubed plus differentiate y raised by 3, that's a 3xy squared y prime. So we see the y prime happens in two places. I have y prime here, y prime here. So those two are like terms, right? So I need to put those two together. So I have x squared y prime plus 3xy squared y prime. Then everything else move to the other side. So negative 3 moves to the other side, become positive. Then this one move to the other side, becomes negative. This one move to the other side, becomes negative. Now, with these two terms, y prime is common factor, so I can factor out y prime. Factor y prime. Then I divide both sides by this term, right? So y prime equals to 3 minus 2xy minus y cubed divided by this term, x squared plus 3xy squared. Right. So that's the rate of change. That's the derivative of y in terms of x. Then if you give me any value, I can evaluate. So this is just live applications, but the process, right, is exactly the same. Okay, I'm going to leave related rates for another video.